Well, that's a little annoying. I just recorded this example 2 of inequality proof by induction, and it all went black and died and it wasn't there. So I'm going to talk you through this again up to the point that we were starting on the proof. First of all, the proof requires another little proof that we've already done by contradiction from page 5. So I've written that down in the blue between the lines there, between the blue lines. The second thing I was doing in the recording was explaining where this proof comes from. So it's 1 on root 2 and 1 on root 3 and 1 on root n. So I decided to use the curve y equals 1 on root x. And if you look at all the rectangles that you can make by starting at 1 and going up to n and doing them 1 unit wide, if you add up all the areas of those rectangles, it's going to be way bigger than the area that's actually under the curve from 1 up to n plus 1. So the area of the red rectangles is bigger than the green shaded area under the blue curve, and that's what the actual proof is. Each rectangle is, the first rectangle is 1 unit high times 1 unit wide. The next one is 1 on root 2 units wide times 1 unit wide. High times 1 unit wide. The next one's 1 on root 3 units high times 1 on root wide. So that gives us our 1 plus 1 on root 2 plus 1 on root 3 all the way up to 1 on root n. And the actual area is an integral, which I've done. It's a definite integral from 1 up to n plus 1. So sub that in and I get the required thing that we're trying to prove. So I've got up to here where we're trying to prove it true by induction. So I'm at the point where I prove it true for n equals 1, and that's where my computer decides to spit the dummy on me. So here we go again. When n is 1, the left-hand side is just 1, but the right-hand side is 2 root of 1 plus 1 minus 1. So it's 2 root of 2 minus 1. So it's 2 root 2 minus 2. Now, we know root 2 is about 1.4-ish, right? So it's approximately 0.8, right? But therefore, the left-hand side, so the left-hand side is bigger than the right-hand side. So true for n equals 1, the base case. So that's the first thing that we might want to do, prove that first case. Now we're going to do the assumption for n equals k. So we assume true for n equals k. Okay, so i.e. we're going, 1 plus 1 on root 2 plus 1 on root 3 plus all the way up to 1 on root k is actually bigger than 2 root of k plus 1 minus 1 in brackets, and just be careful that doesn't go all the way across, it just goes on there. So just looking, check above there, 2 root n plus 1 minus 1, yeah. So we're assuming that that is the case. All right, the third step in one of these is we want to show that it's true for n equals k plus 1 if it's true for n equals k. So we're going to do that now. So i.e. we want to show that 1 plus 1 on root 2 plus 1 on root 3 plus plus 1 on root k plus 1 is bigger than 2 root k plus 1 minus 1. All right, so let's just start off with the left-hand side of this thing we're trying to prove. The left-hand side is 1 plus 1 on root 2 plus 1 on root 3 plus ... plus 1 on root k plus 1 on root k plus 1, isn't it? Okay, and that's equal to, now we assumed this bit here, sorry, I'm just trying to get a different colour. We assume that this bit here, I'll move that up a little bit. was true for n equals k. So we can replace that with 2 root k plus 1 minus 1, that bit in the red, because we assume that was true. And we've got our 1 on root k plus 1. But if we're going to do such a replacement, then this guy is no longer equal, because we weren't doing an equality replacement. We were saying that what we had there in the red was bigger, like what we had there written in blue that's circled in red is bigger than what I've written in red. So I'm going to need to change that sign, and that sign is now going to be that that stuff is bigger than that side. All right, now we just need to work out what happens here. So I indent a little bit here, like compared to where that sign is, to say that whilst there's a greater than sign well up above here in my working, what I'm now doing is equivalence. So the red and blue thing added together is just equal to what I've got here. So this is 2 root k plus 1, 2 root k plus 1 minus 1. And I want to put it on root k plus 1 as well, so we can make a common denominator. So now I've got 2 root k plus 1 root k plus 1 plus 1 all on root k plus 1. So I've just common denominated it. Okay, let's expand that out. That's 2 root k plus 1 times root k plus 1 minus 2 root k plus 1 plus 1 all over root k plus 1. So it's 2 k plus 1 minus 2 root k plus 1 plus 1 on root k plus 1. All right. So we've got ourselves 2k plus 2 minus 2 root k plus 1 on root k plus 1, which is 2k plus 3, which I'm after, because I was told at the beginning I might want to use something to do with that 2k plus 3. In fact, from earlier, we figured that one out, that 2k plus 3 itself, if we go right back to here, the top between the lines, it's bigger than 2 root of k plus 1, k plus 2. 2 root of k plus 1, k plus 2. So I'm just going to put that on this top line, 2 root of k plus 1, k plus 2. I'm replacing the 2k plus 3 with that. Now, 2k plus 3 is actually bigger than what I replaced it with. So we go like this. All right, I'm going to need another page of room here with which to work. So I'm just going to pop in a page break here. And that's the point that I've made it up to. So the next step there will be to factorise, right? So I indent a bit more. So, and this is 2 root k plus 1 into root k plus 2 minus 1 on root k plus 1. And those root k plus 1s will cancel, and it gives me 2 root k plus 2 minus 1, which is 2 root of k plus 1 plus 1 minus 1. So sorry about that phone call in this recording. It'll just be a tick. So that's actually given me the proof that I want, because that's what I was requiring to prove way back at the beginning of this induction step. So the left-hand side is bigger than the right-hand side. The left-hand side is bigger than the right-hand side, and therefore it's true for n equals k plus 1 if true for n equals k. Now I need to then conclude properly, right? So, since true for n equals k plus 1 if true for n equals k, and since true for the base case of n equals 1, right, then it's true for 2, 3, 4, 5, 6, by the principle of mathematical induction, the statement is true for n bigger than or equal to 1. Well, you've got to go back, make sure you conclude according to what the question actually said. All right.